Okay, so we're looking at section 11.1, series and sequences. I'm going to go through these notes pretty quickly. Feel free to pause the video to work on a problem, but I'm just going to work through them. That way the video is not very long. All right, so a sequence is simply a function that's going to generate an ordered list of numbers. So in the first example, in the U.S., average person uses 100 gallons of water a day. We could think of the function f of n as 100n, and it would generate the following numbers. If n was 1, if n was 2, if n was 3, and so on. N being the number of days. We're talking about an average person. So the function represents the number of gallons used on an average day, average person in n days. So you would expect one person in 6 days to use 600 gallons. So this is a sequence of numbers. They're generated by a particular function generally, or some sort of relationship that has some connection to the various numbers. So we input n. We think about n as the input, and we use n. Talks about down here rather than an x. We use n because we're denoting natural numbers or integer numbers that we're plugging into that, rather than we can't say we wouldn't say 2 2/3 days. We could, in real life, but here we're going to be thinking about putting in only integers or natural numbers in for n. Another example might be that you deposit $100 into a savings account that pays 5% interest compounded annually. We could use this function to generate how much money we're going to have after n years. So here, in reality, you could take the money out in a fraction of a year, but here we're talking about it's compounded annually, so we would keep it in for one full year period. So how much money we'd have after 1 year, after 2 years, after 3 years, after 4 years, and so on. And so plugging those in, we would get numbers like this. So you're not always going to have nice, beautiful integers that come out in your sequence like this. This has nice integers that are generated here. These are decimal approximations. Okay, and again, we use n rather than x in this function just to help us realize that we're going to be using natural numbers. X can, generally when you put an x value in, it's a continuous function. Here, this is a discrete function that generates these sequences. So we put an n in sort of to remind us of that. Okay, so a sequence can be either finite or infinite. The finite means that its domain has sort of a beginning and an end. So the n values that you plug in are going to start with 1, 2, 3, and so on up to some value. Okay. In this case, we don't know what that value is going to be, but it's a definitive value. Okay. So for an infinite sequence, then we can think of it as it goes on without end. So we can put in a 1, a 2, a 3, a 4, all the way up to some infinitely large number. Okay, so we call that an infinite series, infinite sequence. Sorry. The resulting terms of the sequence are generally known as. So the first term that's generated, so like this 100 up in this example here, would be denoted as a sub 1. This 200 would be denoted as a sub 2. In this example, 105 is a sub 1. $110.25 would be a sub 2. So the subscript, we're saying a and then sub 1 or sub 2 because those are subscripts. And then the last term, we may or may not know what that actual term is, but we call that a sub n with a subscript of n being the last value, whatever that ends up being. Okay, so the last term is referred to as the nth term. Or a sub n. All right, so let's use some of these ideas to find our first sequence. So we want to find the first 8 terms of the sequence. So we're going to start with an n value of 1. So if I put an n value of 1 in here, I get 1 plus 1 over 1. So that's 2 over 1. So that's our first term in this sequence. And we separate the terms with commas. So now I'm going to put, that was n sub 1, now n sub 2. So 2 plus 1 is 3 over 2, so 3 over 2 is the second term. So we're just going to continue this process. Now n is 3, so it's 4 over 3. You can see it's going to be 5 over 4, 6 over 5, 7 over 6, 8 over 7, and finally 9 over 8. Okay. The next one, again, we're going to start with an n of 1. So n of 1 is 1 over 1, or we could just write that as 1. If n is 2, it's 1/2, then 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. Okay, and the last one, if n is 1, that's just 1. If n is 2, that's 4, 9, 16, and you can see these are just all of the perfect squares, because the function is n squared. 36, 49, 64. Okay, and now sequences can converge, or they can do something that's called a diverge. So in other words, are these terms getting closer and closer to a specific number? Another way of looking at it is, if you look at this function, would this have, if we were graphing this, if this was like f of x is equal to this, would it have a horizontal asymptote? And this one, sure does. You can see probably pretty closely that this thing is going to converge to 1. So it's getting closer and closer to 1. B, that was A. B also is converging. What's it converging to? It's going to converge to 0. And then this one's not getting closer and closer to a value. Indeed, it's getting larger and larger. And so C is called, we say that C diverges. Okay, diverges. All right. Okay, so the next thing that we're going to talk about is whether or not we're talking about a recursive definition or an explicit definition. So when we use the one previous term to get the next term, that is called recursive. And when we define the function, we define the terms without having to know the previous term or terms, then it's called explicit. So these up here were defined explicitly. So for example, I could find the 5th term from this one without previously knowing the 4th term. All right, so that's explicit definition. But here, down here, we define these things what we call recursively. So in other words, I have to know the previous term 4 in order to find the next term. So 4 is the first term, a sub 1. And so if I take the previous term, that was what a sub n minus 1 means. It means if you're looking for the second term, then you use a sub 2 minus 1, or a sub 1, to find a sub 2. All right, so if n is 2, then this will be, the subscript here will be 1. So you would use the previous term 4, multiply it by 2, and add 1, and that gives us 9. And so this is a sub 2. And then to find a sub 3, we have to take a sub 2, multiply it by 2. So we take 9 multiplied by 2, that's 18, add 1, that's 19. So this is a sub 3. And then we take the previous term, 19, multiply to find the 4th term. We use the 3rd term, which is 19, multiply that by 2, add 1, that's 39. So that's a sub 4. And then same process to find a sub 5. All right, so let's go over to this one and see. The first term, a sub 1, is 2. And then what will a sub 2 be? So a sub 2 uses a sub 1 times 3, subtract 1. So that gives us a 5. And so a sub 2 is 5. And then we take the a sub 3, we take a sub 2, which is 5, multiply it by 3, that's 15, subtract 1, so we get 14, that's a sub 3. Continuing that process, if I'm looking for a sub 4 now, a sub 4, I now look at a sub 3, which is 14, multiply that by 3, subtract 1, and that is 41. 1. And then the same thing, a sub 5 would simply be 41 times 3 minus 1, or 122. Okay? Going on to part C here. We know the first term, a sub 1 is 5. So what do we do? Okay, so this one's a little more complicated. To find a sub 2, I take a sub 1 and I add to it 2 times n. In this case, n is 2, so that would be 4. So it's 5 plus 4, which is 9. Okay, a sub 3. So now n is equal to 3 this time, right? So I take the previous term, 9, and I add to it 6. That gives me 15. All right, a sub 4 now. To find a sub 4, use a sub 3, and I add to it 2 times 4, which is 8. So that gives us 23. And the last term, a sub 5. So a sub 5 again. N is equal to 5 now, right? So I take, to find a sub n, I simply take the previous term, which is 23, and I add to it 10, which is 2 times the n, which is 5. So that's 10 more than the previous term, so that's 33. Okay, so these are called recursive because they're using the previous, the formula to find the next term is based on the previous term. These up here are called explicit because I don't need to find the fourth term. I don't need to know the fourth term in order to find the fifth term. Okay? All right, so series now. So series is sort of the next progression in this idea. And series is simply when you take all of the terms of your sequence. So here's an example of a sequence separated by commas, usually how we do it. But a series takes those same terms and just adds them up and figures out what do they add up to. So a series is a sum of a sequence. So let's look at an example. Suppose you start working for someone with a salary of $70,000, and that person promises you a $4,000 raise each year. And then we want to look at what you would make in the first 5 years. So we can think of a sequence as just being how much you make every year, assuming that person keeps their promise of giving you a $4,000 raise. But if we wanted to know how much money you would make in those 5 years, well, then we put plus signs between all those numbers and we would add it up. So the series is equal to $390,000. The sequence is just the individual terms separated by a comma. So the series, those same terms have plus signs between them, and so the series really adds up to a certain value. Okay, so we can have, for example, of an infinite sequence where it goes on forever. ... indicates that's going on forever, so that's a sequence because it's separated by commas. If we wanted to add those all up, we would put plus signs between them. Okay, so we use the term a sub n to indicate a particular term. Here we use s with a subscript of n to indicate the sum of the first n terms. All right, so the sum of the first n terms.